So the first place that one could mention mass spectrometry in a chemistry course is when one is talking about isotopes. Isotopes are, of course, two atoms that are identical in terms of their important bit, their charge on the nucleus, the number of electrons, their fundamental chemistry, but they differ in terms of mass because they have different numbers of neutrons. And because they're identical, it's very hard to tell them apart until you can start to distinguish the atoms in terms of their mass, which is where mass spectrometry comes in. Let's think about boron, okay? Lovely, beautiful metalloid element, boron, that has two stable isotopes, boron 10 and boron 11. So these two differ by 1. Okay, if I was to put boron into a mass spectrometer and look at what is detected, okay, and along here is that m over z, and again we assume z is 1, so effectively that's just a fancy way of saying mass. So mass of 5, 6, 7, 8, 9, 10, 11, blah, blah, blah. Then what we see on our mass spectrograph is we see two peaks, one at 10 and one at 11. Okay, so the mass spectrometer was capable of separating these two cations, the green mark here with a mass of 10 due to the 10B plus, and this one due to the 11B plus. Even more special, however, is the detector can't just detect what ions are there, but it will measure how many of each type of ion hits. Okay, so we don't just see two lines, we see two lines that have different heights depending upon their relative abundance. If you cast your way all the way back to where we first started talking about atoms and isotopes, different isotopes have different relative abundances. So for boron, we wouldn't just see two nice lines here at 10 and 11, but what we would see is that the line at 11 is much bigger than the line at 10. Indeed, the one at 11 is 4 times as big as the one as 10. So what we're measuring here on our vertical axis is essentially just relative height. Okay, we'll talk about that in a little while. Now, of course, looking at this then, we've got our two isotopes. One is 4 times more prevalent than the other. Well, that means that if we think about it in percentage terms, the green one's 20% of all boron atoms, the blue one is 80% of all boron atoms. Put that in fractional terms, 0.2 and 0.8. And so just to refresh you of calculations we did right at the start of the class, that tells us that the actual atomic mass of boron that would appear on our periodic table, which is the weighted average of the stable isotopes, the atomic mass would be 10 times 0.2, because the isotope that weighs 10 is there 0.2 of the time, plus 11 times 0.8, because the isotope that weighs 11 is there 0.8 of the time, and so we will get the atomic mass of boron is 10.8. So these numbers you would have been able to play with all the way long ago. Now we see how we measure those. Let's get a little bit more sophisticated and consider chromium. When you look at the mass spec of chromium, it would look something like this. Okay, masses, I'm picking the particular m over z as 50, between 50 and 52. But now I'm going to plot up the y-axis relative abundance, and we're going to have 100% is equivalent to the highest peak. Okay, so it's relative abundance where 100 represents the highest peak. 100 does not say that 100% of chromium atoms are this peak, but when we look at all the different peaks, the top one we say is 100. And this is how mass specs come back, that the top peak, otherwise known as the base peak, is registered at 100%. Now with chromium, we have a teeny little line here at 50. We have a very big line here at 52, and that's the one that's up at 100%. We have a smaller line at 53, and then we have the absolute baby of them all at 54. Okay, so there are 4 stable isotopes of chromium. That's information you might have been given a long time ago. And the biggest one, by far the most significant isotope, chromium 52. Now when we have a look at the heights here, the blue one, the highest one, as I've said, is 100%. And relative to that, the one at 50 is 5.2%. So in other words, it's about a 20th of the height of this one. The one at 53 is 11.3%. The one at 54 is 2.8%. How could we get the atomic mass of chromium from this? And the answer is you can't say it's 50 times 0.052 plus 52 times 1 plus 53 times 11.3 plus 54 times 2.8, because we're not talking about the relative abundances, we're talking about these numbers relative to the biggest one being 100. And of course, when we talk about relative abundance, as we do for our atomic mass, all of the different percentages have to add up to 100. Here, all our percentages add up to 119.3. So the way we have to go from this somewhat deluding mass spec picture, in which the highest peak is set at 100%, to getting the actual proper relative abundances, fractional abundances of all the different isotopes, is we're going to have to take these numbers here and divide them by 119.3. Okay, so the 100% turns into 0.838%. In other words, about 84.838, I should have said, not 0.838%. So 0.838, in other words, about 84% of chromium is chromium-52. That looks about right. Divide this one by 119.3, and about 4% of chromium is chromium-50. About 9.5% of chromium is chromium-53. And then the little baby one turns into 0.0235, so about 2.4% of chromium is chromium-54. Pop those in to our nice little relationship, and that tells us that the atomic mass of chromium is 52.04. Okay, so I'm not going to dwell on this in the movie. We'll have a few questions like this in the quizzes and on the worksheet, but you do need to realize that the numbers that we're going to use to get atomic masses will come from mass spec, but a lot of times you have to adjust the data ever so slightly.